Let's talk about how the eigenvectors for a matrix are not unique. Strangely enough, different computer programs may give you different eigenvectors for a matrix. It's because the eigenvectors for a matrix are not unique. For example, find the eigenvalues and eigenvectors of this matrix A using A, Mathematica or Wolfram Alpha. Wolfram Alpha is the free online version of Mathematica. So if you enter this eigensystem of this matrix into Mathematica or Wolfram Alpha, you get this. Okay, 8, 8, 8, negative 4, those are the eigenvalues, and these are the corresponding eigenvectors. In other words, the eigenvalues are lambda equals 8 with multiplicity 3, and lambda equals negative 4 with multiplicity 1. These three are the eigenvectors that correspond to lambda equals 8. This is the eigenvector that corresponds to lambda equals negative 4. So again, we get these as the eigenvectors corresponding to lambda equals 8. We get this as the eigenvector corresponding to lambda equals negative 4. Online eigenvector software gives you a slightly different answer. Gives you the same eigenvalues, 8, 8, 8, negative 4, and the same eigenvector corresponding to lambda equals 4. But the eigenvectors corresponding to lambda equals 8 are these. Okay? Mathematica gave us these. These are not the same eigenvectors that Mathematica gave us. Why not? Well, let's review what we mean by an eigenvector and an eigenvalue. An eigenvector of an n by n matrix A is a non-zero vector x such that ax equals lambda x for some scalar lambda. The scalar lambda is called an eigenvalue of A. We are looking for solutions of ax equals 8x because in this particular case, for this particular matrix, 8 is the eigenvalue. Well, x equals 1, 0, 0, 1 is a solution to ax equals 8x, so x is an eigenvector corresponding to lambda equals 8. Any multiple of this eigenvector x is also an eigenvector for this eigenvalue lambda equals 8. Okay, now let's go back and see what's happening. Notice that this vector is just a multiple of this vector, and this second vector, that's a multiple of this second vector. Okay, that might be a clue as to what's happening. So we're going to let y equal 9x, 9009. Again, 1001, that's x. That's the eigenvector we get from Mathematica. 9009, that's the eigenvector we got from some other online mathematical software. So we let y equal 9x, 9009. It's the eigenvector from the online software. I'm going to show you that y is also an eigenvector. Okay, ay is a times 9x because y is just 9x. You can pull out the 9 by matrix multiplication, so that's the same thing as 9a times x. In other words, that's 9 times ax, which is the same thing as 9 times 8x because x is an eigenvector, and so ax equals 8x. 9 times 8x is the same thing as 8 times 9x, and 9x is y. So that just equals 8y. Notice this. ay equals 8y. So y is an eigenvector corresponding to lambda equals 8. Any multiple of x will be an eigenvector corresponding to lambda equals 8 for this matrix. For matrix A, any non-zero multiple of an eigenvector will also be an eigenvector for that same eigenvalue. Now, let's look at another online eigenvector program. The eigenvectors corresponding to lambda equals 8 are these, 1, 0, 0, 1, 0, 1, 0, negative 2/9, 0, 0, 1, 2/3. Mathematica gave us these. Whoa, notice what's happening. These are, unlike what we saw before, these are not multiples of these two vectors. Is there a mistake? No. For matrix A, any non-zero linear combination of eigenvectors for the eigenvalue lambda will be an eigenvector for the eigenvalue lambda. I'm going to prove it. And so that's going to explain how these can be eigenvectors even though they're not multiples of these. So again, let's prove this. For matrix A, any non-zero linear combination of eigenvectors for the eigenvalue lambda will be an eigenvector for the eigenvalue lambda. So the proof. Let's say u and v are eigenvectors corresponding to the eigenvalue lambda. Then au equals lambda u and av equals lambda v. That's the definition of eigenvector. we're going to let y equal AU plus BV. Then AY is A times AU plus BV, which is A times AU plus B times AV. Again, you can just break it up like that. That's just the distributive property. That's going to be A times lambda U plus B times lambda V, because U and V are eigenvectors. So AU is lambda U, AV is lambda V. If we rewrite this slightly different order, we get lambda AU plus lambda VV. In other words, lambda times AU plus BV, or lambda Y. Check this out. AY is lambda Y. So Y is also an eigenvector for the eigenvalue lambda. In other words, any non-zero linear combination of eigenvectors is also going to be an eigenvector. For example, show that the set of eigenvectors from the online software is also a valid answer. In other words, we want to show that this set of vectors, that these are also linearly independent eigenvectors corresponding to lambda equals 8. First, let's show that the vectors are linearly independent. We can't use the invertible matrix theorem, that monster theorem with lots of statements in it, because it's not a square matrix, okay? The matrix that we would form would be 4 by 3, so no invertible matrix theorem here. Let's instead use the definition of linear independence. Is the only solution to C1 times the first vector plus C2 times the second vector plus C3 times the third vector equals 0? Is the only solution to that the trivial solution? Well, the reduced row echelon form of the augmented matrix looks like this. This means the only solution is the trivial solution. C1 equals 0, C2 equals 0, C3 equals 0, bottom row is all zeros. Thus, the vectors are linearly independent. Next, let's show that the vectors are each linear combinations of the vectors. Okay, so this new set of eigenvectors, we're going to show that these are linear combinations of these eigenvectors. In other words, we want to show that each of these vectors is in the span of these vectors here. Okay, so let's first solve this. We have these vectors. Can we show that 1, 0, 0, 1, this first eigenvector in the new set, can we show that it's a linear combination of these three vectors? Well, you can solve that by hand. I mean, you can see that C1 equals 1 and the other two are 0, because 1 times 1, 0, 0, 1 equals 1, 0, 0, 1. So it's obvious that this vector is a linear combination of these three vectors. Next, let's try with this second vector. Is this vector a linear combination of these three vectors? Let's check it out. The reduced row echelon form of this augmented matrix is this one, okay? And so that means the solutions are going to be C1 equals negative 2/9, C2 equals 0, and C3 equals 1/9. And the bottom row is all zeros. Okay, that was great. So this really is a linear combination of these vectors. Lastly, let's solve this one. Is this vector a linear combination of these three? Let's try to solve this. The reduced row echelon form of this augmented matrix looks like this. In other words, C1 equals 2/3, C2 equals 1/3, and C3 equals 0. Great. So this one really is a linear combination of these three. So each of these three vectors is in the span of these. Therefore, the three vectors here, these are also eigenvectors of A corresponding to lambda equals 8. Now, there is another way to do parts B, C, and D. That is to show that these three vectors are in the span here. You just show that they are eigenvectors of A corresponding to lambda equals 8. Because again, we knew that these were eigenvectors of A corresponding to lambda equals 8. To show that these are also eigenvectors of A corresponding to lambda equals 8, that's ultimately what we want to do. Because we wanted to show, that's why we were trying to show that these three vectors are in the vector space of these three vectors. Okay, so let's go ahead and show that those three new vectors are also eigenvectors for A. So A times this first vector, notice what it turns out to be. This is A. You multiply it out, you end up with 8 times this. Oh, check it out. A times this vector is 8 times this vector. So yes, this first vector is an eigenvector of A corresponding to lambda equals 8. And in the similar fashion, 0, 0, 1, 2, 3 is also an eigenvector of A corresponding to lambda equals 8. A times 0, 0, 1, 2, 3, pardon me. You do the math, you end up with this. So it equals 8 times that. Now, we didn't do it for this first vector because you could see that these are the same. So we didn't need to show that that was also an eigenvector. The eigenspace for an eigenvalue lambda is the set of all linear combinations of the eigenvectors for that eigenvalue. For example, find the dimension of the eigenspace for the eigenvectors of A corresponding to lambda equals 8. Again, the set of all linear combinations of the eigenvectors of A corresponding to lambda equals 8 is the eigenspace for that eigenvalue. The eigenspace is a vector space. It's a subspace of R4 because these are all four-dimensional vectors. In this case, these three vectors, they form a basis for the eigenspace. Okay, so every eigenvector corresponding to lambda equals 8 is in the span of these three vectors. So this makes up a basis. All bases of a subspace have the same number of vectors. This number is the dimension of the subspace. The dimension of the eigenspace for the eigenvectors corresponding to lambda equals 8 is 3, because we need 3 vectors in the basis for the eigenspace. By the way, since these 3 vectors are also a set of 3 linearly independent vectors in the eigenspace, this set must also be a basis for the eigenspace. Not a surprise, because every basis for a vector space is going to have the same number of vectors. This basis had 3 vectors. This basis will also have 3 vectors. That's the dimension of this eigenspace.